Oh, I should also point out really quick that a couple of professors were coming up tonight. Yeah, it seems like the sophomores are writing really professional emails lately. What's going on with that? I'm like, yes. That's a good sign. It's better than, oh, these kids, they don't do the work. So you're starting to turn the curmudgeon professors into happy professors, so that's good. I don't know about your physics professors, but I can at least help with the triple E, double E's. IEEE meeting. There's an IEEE meeting tonight in Anderson 21. I've been asked to pass that along to you. I mentioned up here, I promised there would be no TGOs, even though I'll be there. So, and also I think there's the engineering student body is having a free bowling night from 7 to 9 at the bowling alley. So there you go. There's your get out of the lab for one activities.
And there's also free pizza by IEEE.
Oh yeah, so there's free pizza. So, if you recall from last lecture, that what does this specific digital system do? Since you all reviewed this on your homework assignment, it's an adder that does what? Add, subtract. So how are you going to add and subtract? What's the logic? What's physically going on here, and how does it contribute to, there's the physical details of a computer that contributes to its logical execution and are visible to the programmer. What's that definition? Computer architecture, right? So here's how it's visible to the programmer. You have the add sub bit, right? So the add sub bit, if you put in a 1, it'll flip the B input, correct? So therefore, this will allow you to actually subtract the value, and using the same carry-in bit will permit you to be able to do the 2's complement, which is what MIPS uses. So this is a 4-bit adder. So you have the sums on the output, right? And then you have your carry bit at the end. So it's either carry or borrow, so you can do add, addition, or subtraction. So to extend this concept out, are you all familiar with the concept of a ripple carry adder? No? Okay. Well, you're going to learn about it right now. The idea of a ripple carry adder is if you're doing typical addition, right? So if you have 171 plus 246, right? 249. Let me make that happen that way. Okay. So I picked these numbers for a specific reason. So you add these two together, you get 11, right? And then you have a carry. So what's going to happen is every single carry is going to go to the next full adder logic structure. So that's what's known as a ripple carry. So it's going to ripple the carry through the bit. So the longest wire is going to be what goes all the way through here to your sum and carry out, right? So this becomes 12, 1, 2, 4, right? So that's the idea going on there. So one of the drawbacks to this, this is how you learn it in elementary school, the physical implementation. So one of the drawbacks is you have to wait for the carry to propagate. And what's the purpose of MIPS? High performance execution of compiled code. So that's not the most high performance execution, right? We can do better. So speeding up the adder. So what we're doing here is we are actually doing the first 16 bits, and then we have the next 16 bits. Now you notice how bits 16 through 31 come in here, and bits 16 through 31 come in here, right? A and B. So what we're doing is we are doing the same addition here in both of them, except so the carry can only be 0 or 1, right? So this 0 or this 1 here. So it performs the addition if the carry were 0. So we don't have to wait for this anymore, right? Here, it provides it as though the carry is 1, so it does it here. Both sums are sent to this multiplexer, at which point the carry bit, that from this first 16 bits, serves as the mux. So what does the multiplexer actually do?
Choose an input.
Exactly, it chooses an input, right? So you have 2 inputs, and it's going to select one based on your select signal. So in this case, if it's 0, it's going to pick this output. If the carry is 1, it's going to pick this output. So the reason why is now instead of having to wait for this whole calculation, once this gets here, it's already done. So it just puts it on the output. So if you're a designer, what are the pros and cons of this? It's a much larger circuit, right? Because you've got an entire 16 bits here. So that's a con. What's the point? Faster, right? So good design requires good compromise. Here we have an example of that. So now we can keep trying to make this faster and faster. So there's another one here that is a comparison of ripple carry, carry select, and carry look ahead. So these are the three main types of adders. So ripple carry has the slowest execution time. So for those of you who don't, okay, so let me ask you a question. Who in here knows what that notation means? Okay, so just Alex. All right, so that's because I've tortured him in honor sheets. The general idea here is this stands for big O notation. And in this case of n, it means that's the number of execution steps that's required to complete this algorithm in that specific runtime. So this is known as runtime notation. And here we have space complexity as well. So that means that in this case, the execution time, the n represents each calculation of the sum and carry bits. And here, the space complexity represents each full adder. Right? So carry select has an improved execution time. So over the course of the number of bits, it's going to take you big O of the square root of n. So if I were to do 64, I'd just do the first 32, next 32, next 32, next 32. Or I could break it down to 16 bits, or 16, 16, 16, 16, carry, 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 and continue to cut it down. So you can get to the point where you can come up with an optimization there, and that's known as sparsity. And it has slightly larger space complexity. In this case, big O 3/2 times n. Now, this is something if you've taken when you take an algorithms class, you would know it equals the big O of n. Since algorithms is not required for you to know that, in nuclear power school we had a little concept here. We used to call it the I believe button. And you come up with that whenever you're going to learn something in the future, but you just throw out something that is true. So why does that make sense? Okay, well, that would require 3 lectures of algorithms for it to make sense. You'll get there eventually. But for now, I believe, Dr. Morrison, what you've said is true. So that's the I believe button. And the third one is carry look ahead. So the carry look ahead has the best execution time. It actually uses different aspects of the carry. It propagates the wires to generate and propagate bits in order to actually produce the carry bits very, very fast. And it cuts it down to the log of n. They go log 2 of n. So if you have a full carry look ahead adder and it's 32 bits, it's actually going to take 5 calculations instead of 32 to complete the calculation, right? Or the time. So it cuts it down. But you require a propagate and a generate for each one of these, so it becomes n times log n. So you start getting larger and larger. So there's a whole area of research in trying to figure out compromises in space and time complexity for carry look-ahead adders. And the guy who invented the carry look-ahead adder, if you ever look this up, it's they're known as Kogi stone adders. And Peter Kogi, he also is the guy who invented pipeline, which is a concept that we will cover later in this class. He did it while he was at IBM. He is now a distinguished professor at the University of Notre Dame. When I had the opportunity to meet him 6 years ago, and he actually had the first pipeline computer chip just on his. He just pointed out, like, yeah, that's the pipeline chip. I invented it. It's right there. I'm like, yeah, you're a lot better than this than I am. So, So there's a little bit of computing history for you. So does anybody have any questions about this? The reason I've included this as a topic of guide objective is because I want you to understand the whole concept of good design requires good compromise. In an advanced digital system, there's no one right answer. Ultimately, it depends on what your customer wants and what the objective is. So to kind of tie that into what you'll be doing as engineers, you have to understand the objective of MIPS. It's the high performance execution of cloud code. We have this whole philosophy where we work on trying to improve the performance with, by reducing excessive load stores, which we'll go into a lot more detail in section 3. But then every little part of the data path coming into Amdahl's law, we have to make sure that we're optimizing everything properly in terms of both performance and space. So in this case, here we can get a really, really small adder. I'll get to your question in a second. We have a really, really small adder, but it doesn't run this fast. But if we have, it's really, really fast, but it can be prohibitively expensive if the customer doesn't want to pay too much. So, yes.
I'm confused on the O and what is that?
So that's the big O notation. What that basically means is that it requires n calculations here. So if you have one calculation, you have to carry, another calculation, carry. And the reason why I say big O of n is because in MIPS, there's 32 bits, but there's no guarantee that there's going to be 32 bits. Like, for example, in a CISC architecture, you could have 128 bits. You could have 64. In very large instruction board, you could have 128. So this is the reason I phrased it this way in order for you to understand that there's going to be you're not necessarily going to deal with MIPS when you get into industry. So in this case, the big O notation here for space complexity means that I require n full adders. So there's space complexity and time complexity. You have to constantly try to fight between those. Does that answer your question? Right. Any further down numbers, I'd start sending you over to the algorithms class, right? Any other questions before I move on? Yes.
I'm a little confused how this is all visible to the programmer. It seems like
the reason it's visible. This is a good question. So here's why it's visible to the programmer. You have the add sub bits and the inputs. You can code those, right? So this is a really good difference between visible to the programmer and transparent to the programmer. Visible to the programmer means I can actually write code that goes through the architecture, right? The full adder is an example of an organization. How we put this together is an example of the organization. It's those physical details that are transparent, meaning I know that they're there, right? But there's no code that I can write that will change what the full adder actually is, right? No matter what I do, the full adder will always be this. It will always physically be that. But then when we get to the 1-bit full adder circuit, when we get to the arithmetic logic unit, which is what we're building to, you're actually kind of getting to a good point of where that change comes into play. So you have this multifunctional arithmetic logic unit, right? So I can put in an operation bit here. So remember opcode when I was going over in the first lecture with the architecture, right? You have your instruction. Anything that comes out of the instruction, the first 6 bits are your opcode. They then go to what's known as a controller. We'll go over to this in a lot more detail later, but this is just a general overview. The controller determines how we're actually going to have the flow of the calculations go through the circuit. So in this case, what's going to happen here is the opcode comes out, and it's going to go to each bit of the ALU. When you have an organization, that means it's the physical details that you can't manipulate with code. That makes sense? No matter how good of a coder I am, I can't actually change how this computer actually is laid out, right? But these are the physical details, and it's how it's organized. However, the architecture is putting it all together in such a way that I can actually manipulate the code to go through. Yeah, got it?
So you can program it.
You cannot. You can't program a 1-bit full adder, right? But the multifunctional ALU here. Remember when you were? Yeah. Does that answer your question? Okay. So this is where the architecture starts coming into play. This is where you start getting to your advanced digital system, right? So we're building up to what you actually want to learn here in this course. This is what you're paying to learn. But the whole idea is eventually you need to write code, right, you can either do, you all have Java coding experience, right? And some of you, depending on how far you're along, have C++. So we're going to be going a little bit into C, and then we're going to go into System C, Verilog, and VHDL, kind of give you get your hands dirty with those, so that way you can have a better breadth of understanding how coding works. But the whole idea is eventually you're going to compile the code down, because it's high performance execution of compiled code, and it runs it through here. You use the opcode to manipulate which because right now okay, here's a better way to answer your question. Just realize this. So in the ALU, you are actually physically performing all of these operations at once, right? You are performing the full ladder. You are performing NOR. You are performing OR. You are performing AND here, right? So those are examples of an organization, because no matter what, it's actually doing it. But the opcode says, all right, I'm going to send it to this multiplexer, and it's going to choose full ladder, right? Once you're able to make that kind of decisions, that's when you're dealing with an architecture. And that's an important distinction. All right, so now that I've given my spiel on how an ALU works, the other aspect of it we need to worry about is something called comparator circuits. So are you familiar with comparator circuits at all? Okay, so there is such a thing as comparator circuits. How do we actually know if something's greater than, less than, or equal to? So here's the actual logic in TGO 2.11. So if we were to do a truth table, right? C equals not AB, right? So if we had AB 0, 0, 0, 1, 1, 0, and 1, 1, right? So the only int here is A less than B? No. Is A less than B here? Yes. Is A less than B here? No. No. So basically what this is saying is, in this case, when you have A not B is true, that means that A is going to be less than B. So here we have A not, and then B here, right? So that's the only time when A is 0 and B is 1 is when you're going to produce a 1 on that specific output, right? Likewise, the only time when A is greater than B is in that truth table is when A is 1 and B is 0, right? So in this case, you have A is 1, B is 0, because if it's 0 here, it becomes 1, then you AND them, and it comes out there. So in this case here, if you have an instance where, if we know this is when A is less than B, and this is the case when A is greater than B, then the other two times are when they have to be equal, right? So you have 0, 1 and 1, 0 are when you're going to have 1 on this output, right? So here's what's going to happen. If you have 1, 1, this is a NOR gate, right? So that's going to give you a 0. So anytime either one of these is 0, if it's 0, 1, or if this is 1, 0, you're going to 1 on the output, right? So that's how you're actually able to get A equals B. And the reason why this is going to be important in the larger architecture is because we're eventually going to do something called branch instructions. So if you have, if A is equal to B, right? And then there's some sort of code in here, and then there's, some code past the bracket, right? So you have to make some kind of decision as to whether or not you're going to execute the code in there or not. What you're actually going to do is you're going to use that comparison, and it's going to generate a bit. So in this case, if it's A equals B, then we're going to want to have some sort of bit indicating we do a comparison. If they're equal, we want to do the code. If they're not equal, we want to do something called branching past it. So we branch past it, so we use one of these two bits indicating that they're not equal to say we're going to not do that code, and then we're going to set that program counter to the next instruction instead of doing that instruction, right? So that's where this becomes important. So here I actually kind of went through a brief design process. You all remember K-maps from digital systems? I'm bringing back the terrible memories now. All right, so you have the K-maps. You lay this all out here. I'll just kind of leave this temporarily here on the screen. But the general idea is that you're doing the K-map and you're trying to calculate a 2-bit adder. Now, the reason why I included this is you could either just do 1 bit, and then have 3 of these. So then you're adding, space complexity of n, of n squared. The reason why is because if you're doing 4, say D4, then you have to add 2, and then you have to add another one, right? So how do you actually reduce it? So we actually set up the truth table for A is less than B, A equals B, and A is greater than B. We do the K-maps, we come up with the logic, and then we come up with our finalized 2-bit adder. Does that make sense? So here is the actual 2-bit adder. This is A1 and A0, B1 and B0. These are inverters. And so this is B, A1 here. Just redrawing it so that way, in case that I know this can be kind of hard to see. Nice little XOR gate here. Right? And that becomes OR. Same thing here. We have the NOT gates come here. And then we have A1 comes here to this AND gate. Or here, this one comes here. A0 there. B0 not goes there. B0 not goes there. And that becomes A less than B. And then we do the same thing with the NOR gate here. Do you have us A less? Right? So these are now our new calculations. And we were able to do that based on all of this. We did the truth table. These logical calculations are how we actually derive that circuit, right? And so I will leave it there, give it a split second so you can, though you'll probably press pause in the video here. So I'm going to leave 2.13 and 2.14 up here a little bit because this allows me to answer your question in more depth about the difference between architecture and organization. So how does the arithmetic logic actually work in this? So what's going to happen is you have an instruction that comes out. You have a 6-bit opcode. You also have that 5-bit, you have that 5-bit function value, or that 6-bit function value at the end, right? Remember that? We had the zoom in a little here. All right, so we had that opcode, which is 6-bit. We had RS, RT, RD, shift amount, and function, right? And the function was 6 bits. So what's going to happen is the opcode is going to go to the controller and generate a 2-bit control signal, which then goes to something called the ALU control. The function goes to your ALU control as well. So the ALU op, and then that's going to go to the function as well. So what's actually happening here, and to give you a little preview, I think it's 2.15. Yeah. So what's going to happen is we have this ALU operation, which is often called ALU control, and you're actually going to get these inputs here, and those allow you to dictate to the architecture what you want the computer to actually do. So the two inputs to the MIPS ALU are two 32-bit values, A and B. So this is, 32, 32, right? And a 4-bit control signal. That's this guy. The outputs are your 32-bit results. So this is 32 bits here. Your overflow. So if we recall from last lecture, we have overflow bits to indicate whether or not we've done overflow, and we can't guarantee the reliability of the result. And a 0-bit. Now the 0-bit is what happens when we compare the result of the ALU calculation and the number 0. So we'll do that using our comparator circuits. If the value is 0, the bit will be 1. And the reason we're going to do that is because we want to put out there for comparison of branch equivalent and branch not equivalent, which is BEQ and BNE. And we'll go into a lot more detail when we start getting into actual compiling and decompiling the code. So if in the case of BEQ, we're branching if equal. That means if A and B are the same, we'll do some sort of comparison, and then we'll get a 0 bit out there. And then branch not equal, if they're not equal, we'll have a different control signal that controls the rest of the logic, which we'll go into in section 4, but then we also will have a 0 bit on that output as well. So that comes out and goes into the 4-bit controller. Right? So in order to do that, we have a set of calculations here that are in 2.14. So if it's 0, 0, 0, 0, that's coming into the ALU here, then ALU out is going to be A and B. So I'm performing an AND calculation. Else, if it's 0, 1, that means it's OR. So in this case, remember, we have AND here, we have OR here, and we have some sort of multiplexer. So we're doing all the calculations, and these ALU control bits are what are going into your 4-bit multiplexer. So let me ask you this question, since I want to make sure that you all fully understand multiplexers before. I'm going to scroll up and show everybody in the back this as well. If I have 4 bits going into a multiplexer, how many inputs can I control? If I have 4 bits as the control signal to the multiplexer, right? How many potential inputs can I select from? 16. Now, why 16? You are correct. Why 16?
Because with the 4 bits, you would have 4 different input options.
Okay, so you have 4 different. So I think what you're trying to say is 2 to the 4, right? So I can use those 4 control signals to have 16 possible combinations of logic, right? Same thing with the instruction for selecting the RS for the registers. The rate, why is it 30? Why is it 5 bits? Because I want to be able to select 32 from 32 registers. So it's the same question. Do you guys have a question? Yes, you do. What's your question? Don't be shy.
Easy question. ALU CTL or ALU CTL?
ALU CTL, right? It's ultimately an abbreviation for ALU control, right? That make sense? So I want to control what comes on the output of the ALU, right? So it's going to be a 4-bit signal. So this is CTL. Yeah. Is that what you're asking? CTL. L's in Lima. So let me scroll up a little bit so those of you in the back can see the 14 here. Okay, so we've gone over the first 2, right? So now our next else if is if ALU control equals 0, 0, 1, 0, then ALU out is A plus B. And then the fourth one is if it's 0, 1, 1, 0, then ALU out is A minus B. So going back to the what we went over at the beginning of lecture today, you see the difference between those two? An A plus B and A minus B? What do you think? So what's the difference between those 2 control signals? Y'all are way overthinking this. What's the difference between those 2 control signal values? Yeah, it's the second most significant bit here, right? So if I have 0 here for plus and 1 here for minus, if I'm a designer, what can I do with that bit? Where would I want to put that in? Yes, exactly right. Very good. The sign bit. Remember, if we go back all the way to the beginning here where we were talking about our 4-bit adder, right? We can use this add sub bit here, and we can just put in the second most significant bit of the control signal there in order to actually do that instead of having to do extra calculations, right? Very good. So let me scroll back here. And then this second to last one here, if it's A is less than B, then our 0, then we're going to be output 1, otherwise output 0. That's what that notation means. And it's 1, 1, 1. And then last here in the TGO, 1, 1, 0, 0, A or B not. Right? So A not, B not, and that gives you 1 for the logical calculation. So I actually had the solution to the question I just asked written here. So the other notation for this, if you see this, it's also known as set less than. If A is less than B, set equal to 1. So for those of you who have the textbook, that green sheet, if you see the abbreviation will be SLT, because you guys are just asking about what's the appropriate abbreviation. SLT stands for set less than. Okay, so does anybody have any questions about 2.13 and 2.14? All right, so no, it's sufficient to teach what it is I want to teach at this point. All right, so if you recall what I was just talking about a little earlier, we have our 32-bit ALU, right? So if it's an R-type instruction, which means we're performing calculations with 2 values from registers and putting it back into a third register, that's going to be something we'll cover in more detail in section 3. We have the opcode, which is 6 bits. We have a 5-bit RS, which indicates the first register we want to operate on. We have RT, which is the second register we want to operate on. We're using 5 bits there because we can use the 5 bits to tell us which one of the 32 values we use. And then the destination register, which is RD, is 5 bits as well. Then we have that 5-bit shift amount, right? And then the last 6 bits are this function. So we have an opcode, which tells us all the types of instructions that we can do in MIPS for R-type, I-type, and J-type. But for the opcode, only if it's 0, 0, 0, 0, 0, 0, that's all the R-type instructions. We use these last 6 bits from the instruction itself to dictate which type of R-type instruction we want to use. So that corresponds to this FUNCT function. So what's happening here is that we have this function coming from the control signal, and then if these functions, if these 6-bit values are coming out, that correlates to these 4-bit ALU control signals that go to the ALU. So to kind of draw out what's going on here, we have a 6-bit value, we have this ALU control, we have a 2-bit ALU op input, and then we get that 4-bit output. So we have this ALU controller which generates the 4 bits output. So these 6 bits correlate to these 6 here. Does that make sense? And then this output, these 4, correlate to these here. So we have AND, OR, add, subtract, set less than, and NOR. And so the reason I'm doing it this way is to show you that we're slowly building up the full computer architecture, instead of doing it the way that it was taught to me, which was just one day. Let's see if I can. Yeah. Just a little bit of fun. I'll give you guys a quick break here. I know that the notes can be very tedious at times. MIPS, data path, single. Yep, that's it right there. Just boom. You'll know this. I'm like, oh. So what I was just telling you about here, so I'm kind of breaking it down to, so you have a 32-bit output, right? And then the 6 most significant bits go to the control. And then the instruction 50, that's your function. So those 6 bits are going to your ALU controller. And that ALU op was those 2 bits that I was telling you about. So they go here and they make a decision, at which point you have your 4-bit output going to your ALU. So that's kind of what we've covered so far. So we're slowly building to it. So does that make sense of giving you a little bit of, didn't want to just scare you and throw that out there? So I'll give everybody a split second while I'm finishing up writing on this TGO here. 10, 12. All right, so for the rest of this section, we're going to be going over certain types of arithmetic logic and how we're going to use the ALU to actually complete the operation. So we're going to be going over floating point addition, and then we're going to be going over sign multiplication, and then we're going to be going over 2 types of division, restoring and non-restoring division. So we're going to be going over the actual algorithms and going over examples of how to do that. And so the whole goal, you should be able to see how something is being physically done. How do you actually calculate logic using physical objects? So in this case, we have floating point addition. So if you recall, if we're adding 2 numbers together, like you're doing in basic math class, right? And if you add them together, you just put them like this. You make sure that the signs are the same, right? So if you had, 20 and 41, right? You wouldn't add, 20 and 4.1 times 10 to the 1, right? Here times 10 to the 0, because it's not 24.1. That's where. So you have to make sure that your exponents in your IEEE 754 are the same to make those work. So you got to do like some shifting. So this example 2.2 here is an example of how this actually works. So here, what we're going to do is we're going to actually do a 2-bit complement flip of a negative number, and then we're going to add them together, and then we're going to show how the overflow works in this case. So we're going to calculate the sum of 0.5625 and negative 3.75 in binary using floating point addition algorithm. We're going to keep 4 bits of precision during the calculations and represent the result in IEEE 754 format. This is an important thing. I want you to do this on an exam. So if you see, and you practice it enough, you'll start to recognize what these numbers look like. But again, the whole goal is I don't want to exceed 4 bits of precision on an exam. So 0.5625, how do you actually calculate that? That's something that's I get a common question. So if I do 0.5625, okay, so the 4 bits of precision, you're going to have 0.5, 0.25, 0.125, and 0.0625, correct? So what you want to do is you want to take that number and subtract it. So you got 5.625, right? So can you subtract 0.5 from that number? Yes. So that becomes 1. So that becomes 0.0625. Can you subtract 0.25? No, that's 0. Can you subtract 0.125? 0. Can you subtract 0.0625? So that becomes 0.1001, which is what we calculated here. So if you do that, you'll be able to get the correct number every time. So then we have 0.0110 for 0.375. So then, but the question asks for negative 0.375. So then we flip the bits and add 1, and then we have 1. This becomes 0.1010. Wait. Did I do this right? Yeah, there it is. Okay, so sorry, that's wrong. That's correct. Oh, I see what I did here. No, that's just 0.1100 times 2 to the negative 2 is the positive value, right? So then change them so the exponent is the same. 2's complement is 1.010 times 2 to the negative 1, right? So when you add them together here, now if you recall these exponents here, now this is 2 to the negative 1 and 2 to the negative 1. So you have to make it such that one of the original bits is here is 1, right? So if you have 1 there, you add them together. The exponent is negative 1. So remember, if it's e minus 127 is the calculation to the e minus 127. So if you have so this should be equal to negative 1. So this is going to be 126 minus 127. So 126, the best way to know this is 128 is 1 and 7 zeros, right? So this makes 127 that. And then 126 obviously just subtract 0. So that's where we came up with that number. So then you add this number and this number here. I'm sorry, this number and that number. And then we scroll down here. We get the added result. So here's the thing. We have this overflow bit. Now, so if we were just adding the two numbers in this overflow, it just means that we could shift the exponent, right? So in this specific case, this is where having these original sign bits here, we pass them around. So we pass them in here. We have the sign bits. And then if we have 1 and 0, that means we know it's not possible to have an overflow, right? Remember that TGO I presented last lecture about that? So by knowing this, we can actually have this as, we can take this overflow bit, and if they're both zeros, and we have an overflow bit, then we actually have overflow. Or if they're both 1s and we get a 1, that means we actually have overflow. But if it's 0, 1 or 1, 0, that means we know that we cannot possibly have an overflow, and that means this is the result of a negative calculus of a subtraction, which means we can just discard the number. Does that make sense? So that is how we were able to get the correct value there. So these steps, what you want to do is you want to calculate out the binary value, put it such that you have the first bit is a 1, because if you recall from IEEE 754, it's the sign bit, or it's negative 1 to the sign bit times 1 plus the mantissa, right? So the first bit has to be a 1. I'm sorry. So then you just do a bit shift. Every time you bit shift but to the left, you're subtracting 1. So in this case, you have 1.0010. For 0.375, you have 0.0110. You have to shift by 2 to make a 1 the first bit. So you get 2 times, or 1.1 times 2 to the negative 2. Then it's negative, so you actually have to do a sine 2's complement, which gives you 1.0100 times 2 to the negative 1. So you can see here, if we were to do this, you get 0100. 0010 comes from this bit here. We do the exponents, they have to be the same. And then we maintain the sign bits to know whether or not we're adding or subtracting, right? Then from there, we add those together, we get our result. We would get an overflow because we know that you cannot possibly have an overflow in the case of subtraction, and we just discard the bit. In that case, you'll get your actual correct value. Does anybody have any questions about that? All right, so the last thing, make sure you read the directions and represent the result in IEEE 754 single precision format. So now what we have to do is we take our result. We have 0, 1, 1, 0 times 2 to the negative 1, right? We have to get our most significant bit, which was 1, which is there, right? So then we have to bit shift. So it becomes 1.1000 times 2 to the negative 3. Correct? So that's going to be this value that we had here. So then what we do is we put this in our equation. We know it's a positive number. So the first bit is a 0. If it's negative 3, negative 3 is equal to e minus 127. So e is going to be equal to 124. So then we just easiest way to do that is you know that this is 127. You subtract 3, this becomes 0, 1, 1, 1, 1, 1, 0, 0, which is what we have here. And then we take this value and put that as the 4 most significant bits, right? And then what I want you to write on a quiz or an exam, your homework, Mantissa is 23 bits. The reason I'm having you do that is because I don't want you to feel like I have to write 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? But that is sufficient for you to indicate that you actually have that knowledge in your head. And so very quickly, I did the same example here. We did negative 5.625. We took the 2's complement here, 1.1 times 2 to the negative 2. We add those together, and then we get the same carry. And since the sign bits do not match, the most significant bit of the non-overflow is negative, and we get a value there. So I'm sorry, since the sign bits do not match, the non-overflow is negative number. Therefore, we actually do the 2's complement back. Well, no, we have the right answer. That's going to come out as a 2's complement with a negative number, right? So the sign. So you can actually compare the values. If you use a comparator bit, you know that 0.5625 is bigger than 0.375, right? So if you're doing a subtraction and you know that one comparator is bigger than the other one in this IEEE format, you know that you're going to get a negative number. So then you make the sign bit 1. Yes? No. This is the end. Example 2 ends here, where that red line is. This is just, I put this in because this has been a common question in past classes. The common question is, well, what happens? How do you actually, in that case, that problem worked out nice and neat because we had a positive number at the end. Well, what happens if that's not the case? Well, we use the comparator to compare the sizes. We know it's a subtraction, so we know that we'll get a bigger value, and so it's going to be a negative number. So that means our sign bit is going to be 1.
How do we determine the exponent?
Oh, yeah, well, it's the same thing as always, right? So here, our solution came out to be 1.10 times 2 to the negative 2. That's a typo, 2, right? So in this case, it was, since it's negative 2 here, so it's negative 2 should equal e to the minus 127. So that gives e is equal to 127 minus 2, which is equal to 125. And the binary value, remember, if 127 is this, correct? So you just subtract 2 to get 125, so you get 0, 1, 1, 1, 1, 1, 0, 1. Make sense? And that is what we have there. Any other questions? Yes. What? Well, explain what? Okay, well, all right, so do you all understand how I'm doing the exponent? Because I have explained it like 3 times. Okay, so again, when you get to your solution here, this value, right? So 2 to the negative 1. Whatever your value here, it's 2 to the negative 1 there. In the other case, it was 2 to the negative 2. It's 2 to the negative 3. So any kind of result, the exponent needs to be somehow physically represented, right? So in the case of the IEEE 754 is negative 1 sign bit 1 plus the mantissa, which is how many bits? 23, right? Times 2 to the e minus 127. Remember that equation from last class? So this e here should be equal to the actual physical value. So what's happened is negative 1 is your physical value. So the way you calculate this is you get your result and you go negative 1 is equal to e minus 127. Correct? So then you just solve for e. So in this case, it becomes e equals 127 minus 1, which is equal to 126. And then 126 is the physical binary value of this. Got it? Okay, so as a contrary example, here's the IEEE format. So we'll get one more opportunity to do this exponent thing correctly. So you get 0.8125 and 0.25 in binary. So our first, in using the floating point addition algorithm, keep 4 bits of precision during your calculations and represent the result in IEEE 754 single precision format. Show a step-by-step calculation. So step 1, you take 0.8125, and so you have 0.8125, and that's going to give you 0.5 is bigger, so that's going to give you 0.3125, which is bigger than 0.25. It's going to subtract out. It's going to give you 0.0625, so it's going to be 0.1, right? We have that here. And then 0.25 is going to be the easiest one to calculate, 0.100. And so set these there, like so. Now you have to make them equal, because you have to make the exponents equal, right? So then you have 0.1 times 2 to the negative 1. So does that make sense what I've done so far? You have to make these two values equal. So you have to do a bit shift. One of the mantissas has to be 1. So in this case, you get this value here. You get 1.1010, and then you get 0.0100. I'm sorry, 1000, right? Yeah, these together is 0.10001, which is what we have here, right? So now we have that overflow again. But at this point, both of our sign bits from our IEEE 754 inputs are positive, right? Which means we can use that, since we have an overflow, to indicate that we need to shift the solution. So in this case, 1.10 or 10.0010 times 2 to the negative 1 is equal to 1.0001 times 2 to the 0, right? Does that make sense to everybody? Which means we can now put into our IEEE 754 format. Here, I've let out how we're going to do this. It's 0 equals e to minus 127. So that just becomes 127 is equal to e. And 127 is the easiest one to remember, because that's just zeros. And then we have a sign bit of 0. Then the four significant bits are going to be these 4 here, because it's 1 plus the mantissa. So it becomes 0, 0, 0, 1, and then you can put mantissa is 23, Yes.
So for the 0.25, why do you initially just put it at 1.0000?
To maintain to develop the habit that you have to put the most significant, the first one, as there to represent the mantissa. Okay, so that's just practice. That's just me trying to reinforce a good habit. But then you have to shift it over to make sure that the exponent is the same. It's a good question. Remember, oftentimes I'll put more detail than I'll expect. Okay, so those of you who make a quick note, on calculations I'll put more detail, but make sure that you write what you write on your TGOs actually answers the question. So if you, I think a couple of you put just visible and transparent for architecture and organization, those are the only two words you put. So you probably find really quickly that you lost points on that. So make sure that in this case, what you're writing should actually answer the question. All right. So then this is here. I rewrote what we just came up with. Does anybody have any other questions on this? This is going to be kind of a complicated concept, so I understand. Okay, so multiplication and division. So now what we want to do is we actually want to start using this ALU and this adder to actually do, remember we were talking about problems at the very beginning that everything's just a set of additions or a set of subtractions. So now we're actually going to kind of lay out how this actually works. So if you're actually doing a binary calculation, just multiplication, well, in general, what you're doing, the simple version is just, if it's a 1 here, you're just multiplying it. Because remember, we have 16 times 12, right? So you're multiplying 16 times 2 here. So it's going to be 2, carry the 1, it's going to be 3, right? So just 16 times 2. Then you're bit shifting, and then you're multiplying 16 times 1. So that gives you 182. So here you're doing the same thing. You're just multiplying 0, 0, 1, 0. Here you're multiplying it by 1. You're bit shifting. You're adding. So you're multiplying it by 1, multiplying it by 0, multiplying it by 0. And there's your result there. So really this is actually 2 times 3, and our result is 6. Does that make sense? So that's a very simple version of it. And of course the question becomes, with high performance execution of compiled code, how can we make it faster? And I've done this lecture so many times, I actually remember the little questions that I put in there without even looking at them anymore. So here's a general overview of how that's actually done, right? So if you recall, look here, we actually need a lot of bits to represent this result, right? You'll actually need 2 times whatever your n is for this bit. So in that case, it's 4. In a 32-bit, bit input, you'll need 64 bits to represent your this product register. So you have your multiplicand. Oh, I should also reinforce. Your multiplicand is your input number, and your multiplier is the number you're multiplying it by. Right? So in this case, if you have 2 times 4, your multiplicand is 2, and your multiplier is 4. If it's 4 times 2, your multiplicand is 4, and your multiplier is 2. And the reason I say this is because you actually have to physically understand what's going on in the architecture. If I give you 4 times 2 on an exam for assigned multiplication, and you put in the multiplicand is 2 and the multiplier is 4, that shows me at least somewhat level you don't truly understand. So you get a point or 2 off based on that. Okay? So I want you to actually remember and understand that. So here you have your multiplicand, and every time you're gonna start out with the multiplier in the product register. And so every time you're going to bit shift, you're going to left shift 32 times in this case. You're going to shift here, put the least significant bit, and every time you're going to add whether or not it's a 1 or a 0. So if in the case of a 1, you're going to add the result. If it's a 0, you're going to bit shift and do nothing. Does that make sense? So basically, this is physically how it's going on. So if you have in this case, if we reduce this to a 4-bit architecture, we have 0, 0, 1, 0, and your multiplier, your 32-bit multiplier here is your initialized 0, 0, 1, 1. So what's going to happen? First, put in the multiplicand, but you're going to do, it's no bit shift, it's a 1, so it's just going to have 0, 0, 1, 0 there added, right? So then you bring it back, you're going to do a bit shift, check the least significant bit, in that case it's there. So now you're going to add this again, but now it's 0, 0, 1, 0 is the input, but you're going to shift 0, 0, 1, 0 there, and you get 0, 0, 1, 1, 0. That makes sense? So you're actually physically shifting it every time. 2 operations per bit, shift right and add. And then depending on how long your architecture is, that's how many times you're going to do it. So in this case, your multiplication is going to be big O of n. Because it's n additions. But in each addition, so this is, okay, so I'll go a little bit into this. So if you define n as additions, it's big O of n. But in each addition, what are you doing? Think back to what we were doing in the full adder. For each 32-bit addition, for example, what are we doing in the full adder? You're doing 32 little additions, right? 1-bit n. So you're actually, if you're doing n full single-bit adders, and then you do it n times, because it's going to be 32, so that becomes big O of n squared. So that's where it becomes big O of n if you're doing which one? Because you recall which one is the speed complexity is big O of square root of n. Yeah, carry select. So then it becomes big O of n times square root of n. So now that's where you're starting to significantly improve your flow here. And this is where Amdahl's law comes into play. So if you can actually, so if you think of it this way, so let's say n is 8, right? Sorry, let's pick 9 to make this calculation easy. So if it's big O of n squared, it's 9 times 9, which is 81, right? But if you take the square root here, 9 times 3, which is the square root of 9, is 27. You can see even in a theoretical 9-bit architecture how that improves everything. So then you get 32, 64, 128. That's where using carry select really helps you out. All right, so I am going to stop here because sign multiplication is something that should have a full lecture devoted to it. We'll end at 2.3.